Okay, we're very happy to have Maria today telling us about dynamical love numbers for Kerr black holes. Take it away.
Okay, thank you. Thank you very much for having me here today. This is the first time I visit NYU specifically. So I'm based in Utah State University and the IFT in Madrid. But to confuse you more, I'm on sabbatical for the whole year at the Black Hole Initiative at Harvard, where I did my postdocs before I became responsible for faculties. Okay, what I want to discuss today is a topic, if you joined for lunch, that was heated up discussion today without ramen, about love numbers. And so I will present a bit of a context of why we think those are interesting. I will try to tell you what we did with Malcolm Perry, who is my collaborator on this work, and then try to show you a bit what the status of some of these things are. So for those of you not working on gravity or EFTs or amplitudes, maybe you find some other type of interest in why studying tidal deformations is interesting. Even though I have there some review of static love numbers, I will only have one slide to tell you a bit what the ideas around symmetries are in relation to the static love numbers. And I think Sergey has a different view specifically on one of the papers there, but I'll give the references and then we can discuss. And then the third point is related to the paper that I wrote with Malcolm 2 weeks ago, a collaboration that started a year and a half ago. So basically, tidal deformations are very important effects that when we study Kerr black holes typically are not there because we have just a single black hole that is rotating. But the question about tidal deformations has to do with what happens when you place a black hole next to another gravitational object, in particular another black hole which is strong enough to actually deform the first one. So as an example, this would be in a binary black hole context. These ideas of tidal deformations of objects by a gravitational external field has been around for many, many years, actually more or less 100 years. And this discussion is, very well known in stars and in the context of, other planets and systems in the galaxy, and has been one of the main characteristics by which a lot of the people, the astronomers, have been distinguishing different objects and how they are, what is their consistency, right? We know how they squish, we may learn what their internal structure is. So that is part of that idea. Now, the problem is, in particular for black holes, that if we could, and the question is, do first, for example, black holes tidally distort? Yes. What could we learn from them? Could we learn what the internal structure is for black holes? What are they made out of? And how much can they be distorted in some way? Now, for some of us, black holes are just boundaries of space-times, right? They don't have actually content inside of them, like what we have, say, on Earth as internal layers. And so if they're simply boundaries of space-time, why would they deformed? And why would they also have some parameters that could describe uniquely their deformations when we place them in an external field? Yes. The main difference, let me also mention, between a black hole and any other star or planet that has no event horizon is that they cannot be tidally disrupted. Yes. So if a black hole falls into another one, it's a very different process than if we place a star close to a black hole, because the star would be disrupted first and then fall into the black hole. These other two black holes get really squished together and then fall one with each other. So there's a big question about tidal deformation, and that's how I got interested in the problem when you saw probably in the last 5 years or so the problem about certain love numbers. Love numbers, I will define them today for you. Some numbers that would describe the tidal deformations would be 0 for black holes. Yes. So that is kind of part of the motivation, at least for me. So how are these characterized, and do they have some relevant information that we can find for those? So what are we talking about? Like, what is the idea of tidal deformations? Well, we know tides control our soft layers, in particular water, and we have experience of that when you see the different tides and the waves that we see in the ocean as kids, for example. So those are the effects that the moon causes on Earth as an external layer. So it will be the same effect for black holes, but also on the internal structure. I didn't paint it here. Of course, there's tidal deformations to the hard part of our Earth, not only by the moon, but it's very tiny, but also there's the sun as well affecting this. Yes, so this is just one part of the whole problem for the Earth. Another process that happens, which is very interesting, is actually has to do with some of the moons in our solar system. The moon Io in Jupiter gets very, very much tidally deformed by the gravitational field produced by Jupiter, in such a way that it becomes so strong that, because the internal structure of Io is liquid, it has some magma, it squishes it out and becomes volcanic eruptions. So part of the understanding of why Io has these volcanic eruptions has to do with the tidal deformations caused by Jupiter on Io. Very, very interesting results as well have been shown, not only in our solar system, but we now can detect and see information of other moons surrounding other host stars, which look more like a rugby ball or American football ball. And so they are moons that actually have not this spherical shape, but a very squished one. And so tidal deformations can also be measured in exoplanets currently. So there are certain images from James Webb where we have now two galaxies approaching each other. You can see that they're not really touching each other. By gravitational attraction, there's flow of the disks between one and the other. And one of the questions could be, could we measure for the supermassive black holes in each of the galaxies some of those tidal deformations? Could they be present already when there's a merger of different galaxies, not just the binary system for the gravitational waves? So apparently there's a problem to be discussed, or there's this idea around them. And so a simplified model without any disks, without the full story in the galaxies, could be trying to study the problem that is more simple in general relativity, specifically, with no other higher order terms or higher curvature terms in the equations, of what happens with the distortion, the tidal distortions on a black hole system that is embedded in some gravitational background. Okay, so that is what we want to study. So from the pure Newtonian description of tidal deformations, one can think about the tidal deformations as practically gravitational potential where we did the decomposition in multiple expansions. And so what we think can be characterized, or the way this was described, are these dimensionless coefficients, these KLMs, that are going to be the ones specifically defining the coefficients of the tidal deformation of the objects. Yes, so these KLMs, and those were the ones that people used to describe or characterize stars, and were first described by Love, math professor in Oxford, almost 100 years ago. And this is why we call these tidal coefficients Love numbers, or some people do.
Just to make sure, here, this is the property of the compact object, right?
Yes, that is the and only of this object, not the other one. So there's some external field that is not going to be part of the analysis in here. So you have, say, point particle of mass m, and then the other multiples in the expansion would give rise to the deformations of the objects from a spherical, point particle potential.
ELM is the extended field of the second object.
Yes, exactly. But the parameters that are being discussed and the ones that are not going to have any information of the external field and be characterized by the internal structures solely of the object in studies, those KLMs.
And this is a weak field expansion, so this K could be a K of E that then become as a constant term when E small. ELM.
Yes, in this approximation, yeah. So in the same way, one can try to define these coefficients, and in particular, I was discussing black holes, but these KLMs can also be used to describe neutron stars. And as you know, there's no equation of state for neutron stars. So if we could find, these coefficients, maybe we can use them for the equation of states of neutron stars when we study their deformation. And in black holes, that's a big question, whether we can intrinsically characterize the black holes by learning what these coefficients are and knowing something about their internal structure. Yes. So the internal structure question is not something that I'm going to address today. It's just something that is in the background in here. But for the binary black hole system, we know that these coefficients will show up in the gravitational wave forms. And so the reason why the interest has been raised for black holes specifically is related to the fact that eventually we will be able to measure these Love numbers from the gravitational wave forms, okay, in the context of black holes and maybe for the neutron stars. So in general relativity, one can, there are many ways of addressing the issue, but the idea would be to study a black hole solution. Here I put Minkowski space, but you can put your favorite black hole and try to study the perturbations of that geometry that you want to study. And so the problem one wants to solve is, once you have your black hole solution that is solution of your theory, in particular general relativity or pure vacuum Einstein gravity, you would add some perturbation to it. And so this geometry, you can plug that back in the Einstein's equations and linearize them. And so one would find that the perturbation of perturbation equation has an equation like this. And if you do a definition to H bar, and you've probably done that in the past, and choose some gauge choices like this, this is how the equation would look like for you when there is some source that is some external source of matter in your equation. So the problem for tidal deformations, which are going to be encoded in this bit in here, will reduce to understanding the Laplace equation, if you want, or basically your in some curved background that you will create with this geometry here. From these equations, we know that there's, in particular for Kerr black holes, that there's a split in the perturbations that we can distinguish. And so even though these are in principle for the whole perturbations, this is a coupled system of nonlinear differential, in this case is linear equations. Each of the perturbations can be split in 3 different categories. So HTT will become your scalar equation. The perturbations on the TI components will become and have their own separate equations as a vector Laplacian equation. And then the other IJ as being just the spatial ones, separate also independently in another set of equations. So I will not be dealing with all the different types of perturbations, but only related to the TT component of the perturbation in there. And one can then make this assumption that the perturbation that solve a problem of one of the components of the perturbations is basically or behaves like a scalar. So the equation that comes from Einstein's linearized Einstein's equations becomes the scalar equation in the background of the Kerr black hole. Yes, question.
So it's important the metric is stationary.
Yes.
Static.
No, static, not stationary. It's a statement for a stationary metric.
So
The decomposition is
it also applying Kerr.
Say that again?
It works also for Kerr.
It works for Kerr, yes. So stationary implies axis symmetry as well. Yeah, whenever we have a stationary solution, it will imply axis symmetry. Yeah.
You can also say, so what are the boundary conditions?
Yeah. So first the equation, but as always, we need some boundary conditions for that, and I will get to that in 2 transparencies. Okay. So the idea would be to try to make a comparison, and typically we say that the Kerr black holes are characterized by their mass m parameter in A, the spin, but they will be for the tidally deformed also these additional coefficients that we would need to figure out for the problem. So the idea here is then to try just in this paper that we did with Malcolm is to study just the scalar problem. We can change also the spin for that, but s equals to 2 will belong to the case of the gravitational problem that we're interested in. But we can reduce the massless scalar wave equation, and we all remember that it's separable. So there's an ansatz where we can just divide or propose that the scalar equation is of this form, and then decide which are the boundary conditions necessary for the problem. So there are 2 boundary conditions in the problem. One is going to be set up at the horizon of the black hole, and the other one will have to do with what happens at the boundary. A point that I want to mention here has to do with
what boundary?
Infinity.
Infinity.
Yes, the R equals infinity, yeah. So the scalar equation in here has a problem, which is that we don't know how to solve it exactly in closed form. Yes, infinity is an irregular singular point in the problem, and there's a Stokes phenomena happening around that point. So to solve the whole problem, if we wanted to solve exactly the entire problem in not like specific regimes, we would have to solve the problem numerically, and this is part of the reason why Bertie and everyone else, when they're looking at Cassino modes, for example, have to do that entirely numerically. So for the boundary conditions at the horizon, what one can ask is that the radial part of the equation, so when we plug this into the Laplacian, we get different equations, one for the radial bit, the other one with S. So for the spherical or the theta part of the equation, and some eigenvalues for that are these ones here in this question, and these are coupled equations through KLM, as I will show next. But on the boundary of this phase, or at r equals r plus, we will have an expansion of this form, and this exponent here is the monodromy around that point. Yes. So the constraint is basically that at the horizon, one has these solutions that are regular on the horizon. So that's the condition one needs to satisfy. There are different ways of representing. So this is the R plus, meaning the event horizon. R minus is the inner Cauchy horizon, if you want. This is the temperature of the black hole. Omega here is the angular velocity of the horizon. And so this parameter here, the way the expansion around R equals R plus is represented here, is encoded in this way.
Are these waves purely ingoing at the horizon?
Yes. When we have omega dependence, yes. So not for this static case, we can define this as an ingoing only behavior on the horizon for the solutions. Yes. For the static love numbers, when we do the problem for omega equals to 0, then you can still call that ingoing if you want, but this is just regularity at the event horizon.
And what does it mean alpha plus larger than 0 since alpha is complex?
Here, this I think the reason why I put this is for s equals to 0. Yes. Yeah. This expansion, so there are two solutions of the radial equation. One behaves like minus alpha plus, and the other one is with a power plus alpha plus in here.
So there are 4 solutions, because
there are
for each
2.
But for each one, you have 2 choices for plus and minus is.
Yes, that would be the case. But ignore, for this constraint here, ignore this, which is the case of the scalar equation. Yes. Okay. So
you have quadratic equation with 4 solutions.
With 2 solutions.
For non-zero s. For non-zero s, you have 4 solutions.
You have 2 solutions as well. I think the problem is you don't have this bound as being positively defined. Yes. Yeah, this is a second order differential. Okay, and so how do you then read off these coefficients that we were discussing? Well, one can do an analytical continuation, which is a very sophisticated way of resolving the problem, or basically more what we have done is not an analytical continuation in the radial direction or any of the parameters, but just an expansion of R to infinity. Yes, and because the definition or the solutions asymptotically behave with some increasing modes and some decreasing modes in L, the ones that are accompanying these coefficients that are the decreasing part of these equations will be the tidal coefficients, yes, or love numbers.
You don't have the exact solution. You don't have the exact solution for R, right?
No.
You can only solve it
No
either
one
at large
has,
R or small r.
Right. You can do an approximation for small spin or low frequencies, but no one has this. In math terms, this is a confluent point equation with 2 regular points and a irregular singular point, and there's no exact solution currently available. There's a problem with something called the connection matrix. So when you take the solutions to the boundary, there's a Stokes phenomenon. Depends where you're approaching the problem, it will have a different definition for what those coefficients are. Okay, so what happens for Kerr in this problem? Well, these coefficients have 2 parts, if you want. In particular, they have a conservative part, which some people, some groups call explicitly the love numbers, being this part that is the invariant part of the problem. And the coefficients can also have an imaginary bit that will be regarded as part of the dissipative effects of the black holes. Some other people or groups define the KLMs in general as the love numbers, yes. And so they will refer as the conservative and dissipative part as being part of the love numbers itself. So the question for the problem was is very interesting, because one can take the Laplacian equation in here and take omega equals to 0. So that would mean that the external source is a static source. It's not changing in time. That's the interpretation of that. And something very curious happens, because this equation that I was telling you that you cannot solve exactly becomes actually completely solvable. For omega equals to 0, the irregular singular point in r equals infinity becomes regular. And so this equation has 3 regular singular points, and it is solved exactly by a hypergeometric function, okay, for omega equals to 0. So what happens is that if we do that and then try to read off, if we do that, so this is a hypergeometric function, we read off when we do, the boundary conditions correctly, we can read off the KLMs, these coefficients, these tidal coefficients from that solution. And we see that the real part of these coefficients become exactly 0. It's not that there's a cancellation, it's just basically they are 0 because these coefficients become purely imaginary coefficients. And so the question, whenever you see a 0 in physics, this is a super interesting point. So the question was, what can we say, or how can we explain that the static love numbers are 0? Yes. However, as I say, there's a definition here. So there is some tidal coefficient that becomes non-zero, but the interpretation is that this is a purely imaginary bit. And so in here, there is something that is not 0, but this is not the part that is going to be in this love number problem of this love number vanishing problem that Sergey and other groups have worked, okay? So the question was, is there something more fundamental? And so Sergey and collaborators, and I think there are other groups also found later some ideas that maybe there are some symmetries responsible in the case of omega equals to 0. And if so, this love numbers equals to 0 would show up at the gravitational wave data. That would be very, very interesting, because it means some terms should not be there. You could easily distinguish between, say, a neutron star or anything in 4 dimensions that has a horizon or does not have a horizon.
But this static dissipation coefficient, does it have an interpretation? Because it seems a bit counterintuitive. There is no time dependence, but something that decays in time.
Yes. So the coefficient does not, when we set omega equals to 0, for the bit that is the bit that has, I think, let's put it this way. I think we can understand what this number means. The part on this dissipation is not very clear how it would show up in that respect, right? But it would be a dissipation in the sense that if you have your black hole in a static gravitational background, it will deform, but it will not persist if you want the dissipation, the deformation, and it will try to dissipate it away in that sense.
Does it have anything to do that is, is it known if it has anything to do with the super-radian instability?
Well, that's the imaginary part.
The imaginary part.
It flips sign when you get super-radian system. But answering your initial question, so this love numbers, it's really, if you think in terms of borderline effective theory, you look at the black hole from far away, there is leading order action for massive particle, and there are some high dimensional operators. And static love numbers, they just correspond to high-dimensional operators on the world line without static ones, without time derivatives.
And the new, in this case, what would it be? This new LM, the dissipation.
The dissipation is there because Schwarzschild black hole has dissipation, just because the stuff can fall into the, but that dissipation is not static, but then there is frame dragon effect. So from that we know there should be dissipation. When in the rest frame there is dissipation, in the it's not zero omega, now you consider rotating object.
But why is it rotating at omega 0? I'm maybe not understanding the idea.
No, this omega is frequency.
Time.
Yeah, I'm talking about capital omega. So we know that Schwarzschild black hole has dissipation at non-zero frequencies. Now, then when you start rotating it, that implies that just for frame dragon effect, that implies there should be dissipation in zero frequency limit.
This gamma, maybe if I write this, sorry, but gamma is a parameter that is A dependent.
Right.
So this is not Schwarzschild, it is Kerr.
Right.
So it is proportional to alpha, which is A over, and I think it's this in my notation. So dissipation is related to frame dragging in that we are computing that the black hole is dragging its kind of surrounding from an asymptotic boundary.
Don't worry about explaining it to me. I can see this is way over my
I
head.
mean, you can see that there is an R plus minus R minus there. So when R plus equal R minus, like in Schwarzschild, that's zero.
Yeah. Right. So separation between these two, that static love numbers, they're really local counter terms on the word line, which would be generally expected for any particle, right? And these are this imaginary is really the dissipative effects which are special for black holes, which is the statement that black hole is not point particle, but there is intrinsic dissipation there.
I think I still thought Massimo's question was a good one, and I didn't grasp the answer. Dissipation suggests some sort of time scale. And what sets the time scale? Or maybe you don't think it does. Anyway, I don't want to interrupt the talk.
I think, so black holes, if they're not spinning, they're Schwarzschild black holes, they're sitting, they're in space. When they start spinning, these are the stationary ones, so there is an essence of what these objects are doing in time, even though we can study how they deform, in a static background. But independently of the EFT description, the effective field theory description of these objects that I'm not going to be talking, I mean, my computation is purely in gravity. The black holes, the Kerr black holes have an ergo region. So if you watched Interstellar, maybe you remember when the spacecraft was falling into the black holes. So the Kerr black holes have an additional region here that I'm painting, exaggerating it here as being very highly spinning. So if they're the same as the Penrose effect, maybe that rings a bell to you. But what happens is if you're in free motion or free fall motion into a black hole, in this external region for here, you have to co-rotate with a black hole. If you're sitting outside, then not. If you're here, this is called frame dragging. So the black hole, even though it's not the event horizon up to here, there's an additional kind of surface in 3D. You have to think of it as revolving, that it will like drag you, and you would have to co-rotate with the black hole. It is the magical region because we can extract energy from the black hole without touching it, which is kind of super interesting. That's the Penrose effect. And black hole jets will have to do with that, and everything that is falling into black holes will glow because of that region. That's a different one.
But this dissipation is much more general. It's just a statement. You have, think one not about black hole, just you take some finite sized spherically symmetric object which can absorb stuff at non-zero frequencies. That's Schwarzschild black hole, one example. And now ask yourself what would happen if you slowly rotating that object. Because in the rest frame there is absorption at non-zero frequency. In the rotating frame there will be dissipative part in the response at zero
When you speak-
frequency.
I'm really sorry. When you speak of absorption at non-zero frequency, frequency of what?
Of incoming light or incoming
Okay.
perturbation. Because that's what frequency, that's the frequency here. This little omega, that's the frequency of incoming external incoming wave.
Okay, am I doing this time?
I would ask you.
There's a couple of.
Okay, sounds good. Okay, so left numbers are zero in a different way than when I saw the papers, I thought there was some constellations, but actually it's just how we identify them in here. So the real part of those coefficients are really zero. Something that is interesting to see is, whether this dissipation becomes higher or maybe how it changes depending on how fast the black holes are rotating. So what you're seeing here is only this imaginary part of the static love numbers. We fix the mass, and you can ask, we are changing the value of L on this axis, but just looking at this, is that as we increase the spin of the black hole, frame dragging is bigger, but these coefficients become larger and larger and larger. So dissipation coefficients become larger with A. This will change for higher dimensional black holes. There will be a different scheme here, and I will not touch it for now, but that's kind of that. So there's, for trying to explain the zero love numbers, there were two proposals, at least from what I can read. I know Sergey is perhaps has a different view on this. So Sergey and collaborators worked on imposing some symmetries. So what in particular, something called hidden symmetries of the space-time. So we know Kerr black holes have, their solution, the geometry has no intrinsic symmetry, but just the two U1s. But if we write the Tolkolsky equation, or the equation that I was showing you as the linear scalar equation or Klein-Gordon equation in the background of Kerr, one can ignore, or if you want, make an approximation for low spin and insist that in that equation there is some symmetry. Yes, and we call that a hidden symmetry. So it's not a symmetry that is realized at the level of the geometry, it's a symmetry that shows up at this scalar equation that we are looking at. Okay, so there were two proposals for the symmetries, the hidden symmetries, that could argue or shown that there is some symmetry that one can that could in principle explain the zero of the love numbers. And I think in Sergey's and Misha's paper, they call this the love symmetry, but they're referring to a hidden symmetry of the equation, that is SL2R times U1, or another proposal by Lam, Hui, and collaborators in Austin and Luca, where they impose an SO4,2 symmetry for this. Another way of thinking about them, maybe labeling these regions, these are near zone black hole regions in some way. So one can think of them as being an effective, geometry. If we metric reconstruct, if you want, back from the equation, which is the geometry that generates that hidden symmetry. And so those, some people called effective geometries for Kerr. And so one can go a step further and ask, if we impose these symmetries like this, what would be not now the static love number, but the dynamical tidal coefficient? Yes. So imposing this type of symmetries, one can get this effective, if you want, or coefficient. And a very interesting point here is that we have a ratio of gamma functions, which make this a more compact expression. But in particular, what happens is that the dependence of these coefficients that you see here have omega dependence only in 2 of these gamma functions in here. The reason why I'm mentioning this is that there are some regimes in which we know analytically how to solve the Kerr scalar equation analytically. And so in those regimes, what one finds, and this was done in this paper by Sergey and others, based on this Mano Takasuki older paper, is that in fact one can compute the love numbers for small omega frequencies, and one can find that there's a big structure that one finds, but there's a ratio of gamma functions that has omega dependence in not only 2, but actually 4 of these gamma functions in here. Yes. And so here Q is different as well. So this Q is Q minus M omega, and the one found from the low frequency solutions in the paper with the full Kerr black hole, so not any of these approximations had this form over here. Yes.
What does effective mean there? KLM effective.
KLF effective, I mean that we imposed either this symmetry or this ones.
I'm not sure what you mean by say impose the symmetry.
The hidden symmetry. So you take the equation, and you're ignoring, or you're throwing out certain terms.
Well, that's approximate symmetry. That's different from hidden symmetry.
Well, yes. Well, these approximate symmetries, if you want, for omega not equals to 0. That's what I mean.
So by imposing, you mean that there is approximate symmetry? Because
yeah.
This is what we're doing. We're not imposing anything. We're just saying that there is approximation in which there is exact symmetry, which acts.
In the approximation, you want to call it approximation? Yes, you could decide that you want your to realize the symmetry directly, right? You could argue that I want my solutions to be in a representation of SL2R times U1, and for that, you would have to throw away some terms in the differential equation.
Truncation of the equations.
Well, there is,
Which
the equation can be
the-
separated in part, which is invariant in the symmetry and small correction. That's the situation.
Yeah. But there are different ways
You
of.
get the same result for both the.
Yes.
Because
Yeah. You
it's the
get.
same truncation that.
It's a different approximation. This one.
There are different truncations in which you get either SO4, 2 or SO2, times U1.
Right, there are different
truncations.
But if you do that in both cases, you get this dynamical coefficient that you can resolve from there. When you're doing this, what happens is that the irregular singular point, so you could ask, why can I now solve the analytical problem? Basically what happens, r equals infinity is a regular, not irregular, regular singular point. So the solutions to these equations are hypergeometric functions, and we can solve them exactly. Yes, and these are different regimes. But if we insist in using these different regimes for the omega not equal to 0, this is the coefficients that one gets. Yes. In fact, what happens is that these coefficients in here, if we do a low frequency expansion that one can do, will only give you dissipative effects. So there will be 0 love numbers even at omega to first order. Yes, there's a ratio here of 2 gamma functions. This one is not. The ones that you compute from low frequency in the full Kerr black hole will have also non-zero love numbers at first order in omega. So these approximations in here, even though I was just discussing the number of gamma functions that depend on omega, will have a different structure. This will have only imaginary bits in small frequency, in omega frequency, and these ones will have real and imaginary rates. Okay, so the love numbers is a controversial topic. I think some people are still trying to understand, that's what I mean, from what it means for data in the gravitational wave detections, right? It would mean the black holes are non-deformable in some way. And another strategy of doing these computations comes from the effective field theory, which is what Sergey was describing, and trying to think about the problem in a very different context with Wilson coefficients and field theory description of that. So the idea here, and this is, I'm a sabbatical at the Black Hole Initiative at Harvard, and there's Shep Dolleman and all the people doing Event Horizon telescope stories. And so they're like, we want a video for the shadows of the black hole in the center of the galaxy. That's their kind of thing. So that's my video kind of thing of what happens. So the idea is that black holes are in fact dynamical objects. Everything in the universe moves. There's no star that is non-rotating. And we know a lot of stars by now. We don't think anything will be actually static. So the realization of the static problem is interesting as a toy model, but eventually what we want to describe is the tidal deformation. What happens when the gravitational field around the object moves, and what it means for black holes in particular. So the problem that we did with Malcolm was a very different one. It didn't have effective field theory. It didn't have more than just some statements about some approximation that we can do to the scalar equation. And instead of choosing the approximations that are more well-defined in different ways because they have global symmetries and so on in that approximation, is taking the truncation where we have this approximation that is different to the other ones, but keeping not the symmetries that we discussed today before, but just this ones in here. So the equation we wanted to solve is this one that has an SL2R times SL2R approximate symmetry. Yes. And this symmetry was the one that Andy Strominger and Alejandra Castro and Alex Maloney used in the past for the Kerr CFT description, where they wanted to link the problems to having a CFT description of the Kerr black holes as well. So we used that one again in here, and try to answer the question again, can we solve this equation and compute the love numbers from it, and see what we get when we compute or go to the low frequency regime. Yes. So in this problem, we are also going in some way to make R equals infinity to become again a regular singular point. So the solutions are going to be hypergeometric solutions. They're different in the near zone approximations that the other groups propose, but that was what we proposed here.
Is R goes to infinity accessible in this regime of
it will be, there will be, yes, exactly.
Omega, how doesn't R have to be finite? Omega is non-zero and omega R is very small.
Right.
R has to be finite, no?
Yes. This in this approximation, yes, in this zone.
Then you cannot get R goes to infinity.
There is an R equals to infinity in the near zone approximation as well. And the so you can let's do this. So you can solve the problem if you want just within this region, where R equals infinity in this region is not the R equals infinity of the Kerr black hole.
Okay.
So in some sense, you're chopping, I don't know how you want to. So there's a black hole somewhere here, there's a throat, and let's call this, I kind of the radial direction in this way. If you want, you're by doing that, you're in a region close to the black hole, where now in your new region, there's, let me call this near some infinity. Yes. What you want to do next is to go to r equals to infinity for, say, the Kerr black hole. Yes.
That's it.
Okay.
But when you say that you using the symmetry,
Don't laugh. We are not. I'm fine with this, but yes. Tell me, Sergey. Yeah. Okay.
no, so what do you exactly mean when you say that you impose in the symmetry using symmetry? It just means that you use this truncation, right? Which happens to
The
have,
solutions are hypergeometric solutions.
but there is no symmetry, right? Because that symmetry, in other words, solutions of.
Don't go to solutions. We discussed that. Yes, I agree. This is not true. The only reason why I'm calling this SL2R times SL2R because there's an interpretation that we can do that has to do with a CFT description, if you want, where we can identify that related to a CFT. I agree with that. The solutions of these equations will not be in the same SL2R tower.
I'm just trying to understand what you're doing.
No,
So you're really just looking at this truncation. You're not
Yes.
using in any way SL2R
No.
plus SL2R symmetry.
And these three different truncations of the wave equation have been shown by Lowe and collaborators to be the only three ones that you're allowed to do if you insist in having at least one SL2R. Do you agree?
Not quite.
Okay.
Because these SL2Rs in this truncation,
Mm-hmm.
they're not globally, they don't correspond to globally well-defined Killing vectors.
Right.
But those SL2R, which in those other truncations,
Mhm.
they're globally well-defined.
Yep.
So in that sense, this one is different.
Right. Yeah.
Okay, so I don't understand. The truncation is up to terms that are of order mw cube, because here you have terms that are of order 0, 1, and 2 in m times w.
And they're
which is a
omega
small
squared terms as
Yeah,
well.
so
In the other two proposals, there's no omega squared terms. They cancel. So the equation looks very much the same. I can show you later, but so we are keeping still some omega squared terms in both of the other symmetries that are globally defined. Their approximation has no omega squared terms.
And so you have thrown away terms that are higher order in m.
Yes, exactly. We can look at the equations and see that more. I didn't include that here, but it wasn't on purpose. It's just I don't know, I didn't have time. So okay, so what do? We take that truncation, and there's for being in this game, one has to do a coordinate transformation and identify some things, and you end up with a hypergeometric equation in here. And so the game is then how to identify the KLMs on the boundary. So if you go to the paper that Alex and Andy did and Alejandra, you can see exactly this expression for the solution of the equation. What was not done very correctly was what happens at the boundary. So what ends up happening if one is very careful about the parameters that one is using is actually that when one does the expansion of the solution, and here there's no analytical continuation, this is just simply a Taylor expansion at r equals infinity, is that there's a log term. And that will be relevant for the love number identification as well. So we can do that in this approximation and read off what the Tidal coefficients are. And all of the ones that you get from playing this game have this log in them. And moreover, what ends up happening is that we get the gamma functions in the same way or with the same dependence in omega in the 4 gamma functions that this low frequency full Kerr black hole solution was showing. Yes. So if we do a small spin or a small frequency expansion in here, we start recovering not the SL2R times U1 or the SO 4,2 expressions for the love numbers, but for some reason it's finding or describing the dynamical love numbers for the honest low frequency for full Kerr description that came from the original paper of the Japanese group that then Survey and collaborators clearly showed. So before finishing, because I know we are kind of over time, the only thing I wanted to mention is that in this way of representing the dynamical love numbers, if we do an expansion in omega, one can see that there's a pattern actually on all the different, so the love numbers, the dynamical love numbers are not zero, but they become dependent one of the other, and they're all proportional to the zero dissipative part of the coefficients, yes? And there are some statements. So in particular, this statement that caused apparently a lot of feelings to other groups because we are not finding some terms that are present about rigidly rotating effects in this approximation. So that's one of the things we see there, and disagreement agreement with the low frequency results, which is exactly what you see in here, which is this expression that shows up in the low frequency regime.
What's the physical meaning of this law?
The what?
The physical meaning of the law.
Basically, so what happens is in practice, so for the love numbers per se, this will mean that there's some scale that one has to fix for them. So you would have to be measuring at some point in your space-time at r equals something. And those are some scale, effective scale that you will put in your problem.
Well, this correspond to, in practical languages, correspond to high-dimensional operators with now some time derivatives. And just the statement there is running, there is log running.
But in the static case, there is no log running, no?
Right, but these are not static.
These are the non-static ones.
Omega.
But in the omega to zero limit, there is free.
No, but they vanish in the omega.
Yeah.
They vanish in the omega to zero.
Yeah.
Okay.
Okay, so we made a comparison with some papers in Eric Poisson's paper. So there's a different way of doing all these computations, and if you talk with the astrophysics, the theoretical astrophysics, Eric Poisson or Alejandro Bonanno and Amor, etc., they do something called post-Newtonian approximations for that. And one can read of the different coefficients. So they really do, the expansion of what the tidal deformations are and solve the full Einstein's equations in all the regimes. And one thing that was interesting to see on this is for the static case for Schwarzschild was that actually the prediction of the love number, that is, this dot here means dependence on omega to first order, has this structure. And when we compared in the limit the coefficients that we were getting from our approximation, if you set r your scale to certain value meaning that this is 1, you get exactly the coefficients that they get from the post-Newtonian approximation in here. So there's some link which we cannot establish, and I think it would be interesting to understand how post-Newtonian computations are done. And in general, if there's a good reason why, we could do the computations maybe more effectively than what they're doing in the post-Newtonian approximations there. So this was the statement here. And for us, the interesting bit as well was trying to think about these love numbers in the context of the CFT. So we still think that Kerr CFT is there. We could think that these love numbers will have some interpretation in a CFT dual. There will be some way of thinking or computing them from there. So one can actually identify some left moving and right moving sectors, so some SL2R left times SL2R right sectors, and try to think about what these coefficients mean, the log numbers in the context of the CFT. There's no big statement there, it's just, you know, a way of identifying how they would look like. We haven't identified specifically which CFT is one.
But there is a lot again. I was asking, the logarithm doesn't look like very CFT-like.
Yes, yeah, but it's still, you know, there, yeah. This will happen as well for all the Kerr CFT story. So if you go back to the papers, there were some logs that should be there and were not relevant in the regime where you're looking at the CFT description, but these logs should be there if one does that carefully enough.
Sorry, I got a little lost. What is R in this description? Because now you're talking about the coefficients, right?
Right. R is your distance, if you want, your radial distance to a certain boundary, call it the horizon.
So these K are not coefficients in the expansion of the multiples, because they also depend on I misunderstood it. I thought that you had, you expanded the field in multiples, and then you had numbers,
Right.
I mean, constants. But instead here you have functions of R.
Yes, they are log functions of R. So you still have the R to the minus L, but these are multiplied each term by a log function.
So it's another way of saying that there is random.
So one can generalize and replace some of these R plus or minus for other solutions, Kerr-Topnut and some alternative theories of gravity. I think here you would get the same expressions for the dynamical log numbers. These Kerr-Topnut stories, if you followed all these Kleinen stories that Andy has been doing and Adolfo Guevara and so on, self-dual, I don't know if that rings a bell, will have to do with these cases as well. So there are some interesting things coming up in that direction. And I think that's kind of everything I wanted to say today. So I guess it's pumpkin time. Maybe black holes are actually like pumpkins and we can squeeze them and see them that they have different shapes. So that's the end of my talk today.
When you said that other groups had strong feelings about Kerr being not exactly point-like thing, what did you mean? Because our group calculated it, right? So we said that it's not point-like. So there was
not point-like in what sense? I mean
there is dynamical response.
Yes. So what I'm saying is that we don't get those terms in our approximation, and the terms that you see for the rigidly rotating body. So
no, I'm saying about full response. Full response is there.
Yes.
So Kerr.
No, but I didn't mean that. The only thing I meant is there's a term that you get that has no log term. Is that maybe, Sergey, what? Maybe I said it.
But you had a comment when you calculated tidal response for Kerr.
Yes.
Saying that these numbers are
not
the answer.
The previous one, the next one.
The back here.
Yeah, Kerr black holes do not universally behave like rigidly rotating
dissipative
spheres.
So there's a term for showing that.
Yeah, but I think we never disagreed with that, and we calculated those terms, right?
What I'm saying, we don't get that term. You get that, you computed it. Is that?
So this statement, Kerr black holes do not universally behave like rigidly rotating dissipative spheres.
Yes.
That's what you get.
That's what you guys compute and get. What I'm saying is, in our approximation, we don't get that term.
Okay, and so what is the statement that you're making?
I'm just saying that if you do an SL2R times SL2R computation or our truncation, we don't get the full story about the rigidly rotating black hole. That's the only statement I'm making.
So what does it mean in terms of these coefficients? It means
Right.
that they get some extra in K1, K2.
So correct me if I'm wrong, Sergey. I'm trying to understand. I'm not making.
No, I was just trying to, because you apparently made some comment about our feelings, and I'm trying to understand what.
Well, I don't know. It has been like a long 10 days of things in the background, so I don't want to. I was going to delete that, so I didn't. So there's a term that you get that has some form like this. Maybe I can pull up the right. Is this? There's some coefficient. There's a RS probably here as being 2 times. In my notation is 2 times the mass.